Welcome to Module 1 of Lecture 6 of the course VLSI Design, Verification and Test. In the last few lectures, we took a look at resource constraint and time constraint scheduling strategies in high-level synthesis. In this lecture, we will look at an important post-scheduling step, allocation and binding. So what do we have at the output of the scheduling step? At the output of the scheduling step, we have distinct time steps assigned for each operation. So we have a scheduled operation constraints graph. Here we have an arbitrary operation constraints graph. In this graph we can see that the operations plus multiplication and adder here is performed in time step 1. In time step 2 we perform this multiplication and this addition. In time step 3 we perform this multiplication, and in time step 4 we perform this addition. All these are unit time operations. Each of these operations take input from certain input variables and produce outputs on temporary registers or temporary variables. So these T1, T2, T3 are temporary variables. And what we have is a set of register transfers. The set of register transfers here are T1 equals to x plus y in the first time step, T2 equals to x into z in the first time step. Similarly, we have different register transfers at each time step at the output of the scheduling step. Now, after we have assigned a time step to each operation, our job is to actually allocate and bind physical components to the RTL transfers. To the operations, we need to assign functional units. To the registers, temporary registers, we need to assign actual hardware resource registers. We need to steer the outputs of the registers to the appropriate functional units, and again we have to drive the output of the functional units to appropriate registers to effect each register transfer. So therefore, we need to assign physical components to the register transfer level design. Now, in most cases, scheduling gives us an estimate of the resource usage. So in latency constraint scheduling and time constraint and resource constraint scheduling that we had looked in scheduling, all these scheduling algorithms took an estimate of the resource usage, a bound on resource usage, bound on latency, and provided us a schedule. Now, the work of the allocation step is to minimize and find the actual numbers and types of resources that will be required. And this will be done via appropriate register sharing, resource sharing. What is sharing then? Resource sharing, the assignment of a resource to more than one operation. Now, when we do resource sharing, we need to keep various issues in mind. For example, let us consider the case of functional units. So the same functional unit can execute multiple types of operations, say. That means that in the scheduling step, we saw that the comparison operation, the plus operation and the minus operation all being performed using the ALU. So I can have multiple operations being scheduled by the same resource. And then I can have a resource that can execute multiple operation types. So there we are saying that multiple a resource, the same resource can execute multiple types of operations. Now here the same resource can execute multiple types of operations, but it comes with a cost. For example, let us say that we can combine a multiplication and an addition as an example. However, the addition, the combination of addition and multiplication comes with a cost, because it requires a more complicated functional unit, say. So we can have simple adders that can perform only additions, simple multipliers that can perform simply multiplications, and I can have combined adders and adders as well as multipliers which can do both, but possibly these combined adders and multipliers take more area than simple adders and simple multipliers. Now, if the objective of your resource binding is to arrive at a minimum area design, then what do we have here? Now, because we have a combined multiplier and adder, then these two operations become compatible, meaning that if multiplication and addition is being performed at two different time steps, then such multiplication and operations can be combined and implemented using a same resource instance. However, this comes at a cost. That means that what will be the minimized area design will depend on how many combined multipliers adders you are using, how many multipliers you are using, and how many adders you are using. Let us say previously you used only simple multipliers and simple adders, and therefore previously you could not combine multiplication and addition operations in the same resource or functional unit. However, now you are being able to combine multiplication and addition in the same functional unit. So, what you are having now is additional resource sharing. Now, higher resource sharing means I am reusing the same functional unit more. That means I can possibly reduce the area of the circuit. However, what will be the effective improvement? Now, due to higher resource sharing, I have probably reduced the number of simple multipliers and simple adders. Let us say the total area cost due to this reduction, the reduction in area due to the reduction in simple multipliers and adders is x. However, there is an increase in area because we said that these combined multipliers and adders take a higher area than simple multipliers and adders. And let us say this increase in area due to this combined functional unit is y. Then what will be your effective gain in terms of area? It will be x minus y. So, we have to find out. So, there are issues. What I am trying to point is that there are issues. Choice of what allocation choice you will have, what resource sharing you will have, what resources you will choose for which operation is a complicated problem. This is what I am trying to point to. Another example is that an operation type is implementable with multiple resource type. So, the same operation type is implementable with multiple resource types. For example, let us say you have two different types of adders for doing the addition operation. Now, adder A is higher in performance than adder B, but adder A also takes higher area than adder B. Now, given a resource assignment problem with a bound on latency as well as your area, the choice of the numbers of adders, adder A and adder B in your design will depend on how you optimize both area and performance, area and latency. So, again what I am trying to point out is that the problem of allocation, that is finding the appropriate and correct numbers and types of resources for each operation, for the different operations, so that my design objectives are met, is a complicated problem to solve. There are a lot of choices to make. Now, a distinct allocation choice for a given type of resource may have effects on choices of other resources. Now, I have chosen, let us say, for example, I have chosen a certain number of registers for implementing, for allocating the variables in my schedule, the temporary registers in my schedule, and I have also decided on the number and types of functional units that I will use to implement the operations in my schedule. Now, given a choice, a particular number of registers and particular allocation of the registers and a particular type and number of functional units for a given decision, your steering logic, that is the numbers and types of muxes and demuxes, will depend. For what will these muxes and demuxes do? Muxes arbitrate write accesses to functional units and registers. On the other hand, demuxes arbitrate read accesses from functional units and registers. So, a choice of which register, which variables you have put on which registers, which operations you have mapped to which functional units, will decide on what will be the number of muxes and what will be the types of muxes, a 4:1 mux or an 8:1 mux. The choice of types and number of muxes will depend on the choice of registers and functional units that you have made. It will also make it will also determine the control circuits that you have. For example, now the number of control outputs that you will produce will depend on the types of numbers of muxes and demuxes. Let us say the selective inputs of the muxes and demuxes are controlled by these controllers. So, when the number of muxes and demuxes change, numbers and types of muxes and demuxes change, the control circuitry, that the number of outputs that the control unit will have to produce at each time step, that will also vary. So, the register and functional unit allocation step will also determine what will be the complication or in the control circuit. It will also affect the wiring in the circuit. What will happen? Let us say you have buses in your circuit and your registers float their output on the buses, your functional units also float their outputs on the buses. Now, a bus line can only carry a single variable, a single data at a given time. So, depending on the numbers and types of registers, muxes, functional units, what will happen is that your number of bus lines will be determined, and hence a choice of registers and functional units will also determine what will be your wiring, how complicated will be your wiring, right. So, therefore, what we conclude from this discussion is that the overall area, performance and power consumed by the circuit will depend heavily on the choices of allocation that you make, and hence the allocation problem is an important problem to solve as optimally as possible. With this introduction, we now define resource binding. What is resource binding? Resource binding is the explicit mapping between behavioral operations and resources. So, you can have many instances of these resources. For example, let us say we have 5 multipliers in a design, multiplier 1, multiplier 2, multiplier 3, multiplier 4 and multiplier 5. Each multiplier, say multiplier 1 is an instance of a resource, multiplier 2 is an instance of a resource, and each resource instance, multiplier 1, let us say, will be mapped to a number of behavioral operations at different times. Now, resource binding is therefore the explicit mapping between these behavioral operations and resource instances. Now, with this definition, we first characterize resource sharing and binding problem with a simple case. Let us consider resource dominated circuits which have been scheduled under resource constraints. So, we have done resource constraint scheduling during my schedule step. So, therefore, the area is already determined by the resource usage, and therefore, I know the number of functional units that will be required. Now, binding in this case, binding and sharing in this case will therefore just be to refine the structural information so that the interconnection synthesis can be performed. By interconnection synthesis, I mean, let us say, subsequent allocation and binding of subsequent resources. For example, we said muxes, buses, control units, etc. Right. So, when we have done an actual functional unit to behavioral operation mapping, then only can we do the subsequent synthesis, solve the subsequent synthesis problems for muxes, buses, etc. In this here, for simplicity, we assume that all operations and functional units are of the same type. Let us say that so what we are doing here, we will characterize the basic resource sharing and binding problem by understanding what its ILP model is, like we did for the scheduling problem. Now, to start with the ILP model, again here we need to define a set of decision variables. So, what are the decision variables here? The decision variables are a set B, where it contains many decision variables of type BIR. Now, what are these indices I and R? I goes from 1 to n, the number of operations, and R goes from 1 to dot dot up to A, the number of resources. Let us say A is a bound on the number of resources, and I are the operations in my operation constraints graph. Now, BIR equals to 1, that implies that operation Vi in my operation constraint graph is bound to resource instance R. Now, A less than n is an upper bound on the number of resources. Now, because we have already conducted scheduling, my decision variables that I had for scheduling, they have now become decision constants. These x's have now become decision constants. What do these x's tell me? These xil gives me the start times of resource I. When this xil equals to 1, it means that operation Vi starts at C step L, and that step L is given by Ti, right. So, we saw these decision variables and how these start times are obtained in the scheduling step. So, now they are decision constants, meaning these values of these constants are known to me. When each operation will start at what time step is now known to me at the allocation and binding step. So, with this we come to the formulation of the constraints. To obtain a binding, we search for a set of values of B such that means we need to obtain a binding, that means we need to allocate the behavioral operations to the resources such that a set of constraints are met. And what are these constraints? The first constraint is that each operation should be assigned to exactly one resource. How do we write this constraint? For R equals to 1 to A, summation BIR, that means for each operation I goes from 1 to n, this has to be true for each operation. Now, let us say for the ith operation, let us say for the first operation 1, B1R should be 1, where R goes from 1 to A. That means operation 1 can be scheduled in only one and one, exactly one of these A resources that I have. Only then will this summation be equal to 1. So, operation 1, because B1 I am considering, can be assigned to at most and exactly one operator type or resource type, and hence for over all the resources, summation over all the resources, this value BIR will be equal to 1. The next constraint is that at each C step, at most one operation among those allocated to resource R can be executing. So, what does this tell me? That for each resource R, so we will take one resource at a time, and for that resource we will consider for all time steps. For each resource we will consider all time steps, and we want to constrain, we want to provide this constraint that a single resource should execute at most one operation, 0 or 1, at most one operation at each time step. The resource can either be idle at that time step or can execute at most one operation. It cannot execute multiple operations at the same time. A single resource cannot execute multiple operations at the same time. So, this is what this constraint restricts. And how do we write this constraint? The second part of this constraint, this term here, this term should be familiar to you from the scheduling step. What does this term tell me? It tells me whether at the current time step this operation is currently under execution. So, summation m equal to L minus di plus 1 to L x I m will be equal to 1 if operation I is currently executing at time step L. And when will operation I be executing at time step L? If it has started at most di time steps earlier to L. That means, at L it will be executing if it has started at most di time steps earlier than this. If it has started even earlier than di time steps from L, then it has already finished. If it has not started after di time steps, then it has not started at all. So, and it is not executing. So, at the current time step, operation I is executing only if it has started at most di time steps earlier than the current time step, and this value will be 1 when operation I is executing at the current time step. Now, we come to the first term here. What does this first term tell me? I equals to 1 to n b I r. That means, for each resource r, what do I want to determine? I want to find out what this term, if you see in seclusion, this term will give me all operations that are bound to resource r. Because we are doing this whole constraint for each resource at each time step, then if we take this operation, this term in seclusion, this will give me all operations that are bound to resource r. And when we multiply this term with this term, it gives me all operations that are bound to resource r and is actively executing at time step L. So, this gives me all operations, this gives me whether an operation is active or executing at time step L, and this term gives me all operations that are bound to resource r. So, the multiplication of these two terms will give me all those operations bound to resource r and are currently executing. Now, there cannot be two operations at a given time that are bound to resource r and are both executing, and hence this value, the multiplication of these two terms, has to be less than equal to 1. Therefore, we get what we want. At each C step, at most one operation among those allocated to resource r can be executing. And the third constraint says that these decision variables are binary. It can either take 0 or 1. Using this ILP model, we will be able to get an appropriate mapping of the resources to the operations. Thus, with an understanding of the basic ILP model for resource sharing and binding, we come to the end of module 1 of lecture 6.